This is the paper Reachability in Dynamical Systems with Rounding. This is joint work with a lot of people from the Technical University of Dresden, IRIF and the Max Planck Institute for Software Systems, under the guise of the Centre for Perspicuous Computing. We're going to reconsider the well-studied problem of reachability in a dynamical system. However, the key difference here will be that the dynamical systems incorporate rounding at each step. Let's consider what we mean by a dynamical system, and then we'll introduce what we mean by a rounded dynamical system. In our setting, we have a linear update map represented by a matrix. We start from a point in space, here represented in 2D space, and we go to the next point by applying our linear update map. This means we apply matrix vector multiplication, applying the matrix to our first point. This generates the second point in our sequence, and we create a sequence of points by continually applying the matrix. We call this sequence of points an orbit. The 2D dynamical system shown here is partly a rotation and partly some scalar. This means that in each step we rotate about the centre coordinate by some angle, and then we scale in the x-coordinate by 1.15 and then the y-coordinate by 1.05. And you see that this starts to define an expanding spiral. The classical reachability question is whether this orbit will ever hit a particular point. So, for example, we could ask, do we ever hit the point y? As we start to go past y, we notice that we miss y. And since we've missed y and we're expanding, we know we'll never come back to y. So why are we interested in dynamical systems? These can be used to model computer programs, and decision questions about them can answer questions about the behaviour of the program. For example, reachability in this system answers whether the guard condition is ever met, and thus whether the program ever terminates. However, real computer programs do not operate with arbitrary precision, as assumed here. They are restricted to finite memory, and computations must fit within this space. And therefore, at each step, rounding is used, at least implicitly, and this keeps the numbers in the finite precision allowed. We study the problem with this rounding forming part of the behaviour of the dynamical system, and in this way we hope to study more realistic behaviours, and therefore we define the point-to-point reachability problem for rounded dynamical systems. So the rounded dynamical system moves to the next point, but then remaps to the nearest grid point. For the next point, we rotate by applying the matrix, and then we round. We rotate, and we round, and so on. Now we can ask if this different orbit is going to hit the target y. Indeed, this orbit does hit the target y, and so this introduction of rounding leads to a different answer to our reachability questions. So let's take a look at the different ways we might round numbers. Some of the most common ways in computer science to round numbers is the floor and ceiling function. Similarly, one can also consider the nearest rounding function. So for example, this takes 2.2 to 2 or 2.7 to 3, but we have to tie break on what 2.5 does. However, our analysis will quickly need complex numbers, and so we need to decide how to round complex numbers. One way to do this is to consider a complex number as both its real and imaginary part. So x is represented by a plus bi. We can then round a plus bi by rounding a and rounding b separately. Representing this in the complex plane, this corresponds to rounding to the nearest grid point. You could use any rounding function you like on both a and b. Another way to represent complex numbers is to use polar coordinates. Here a is represented by its modulus and its angle from the axis in the complex plane. We can then round a, the modulus, and theta, the angle, separately. And so here in the complex plane, x is rounded to its nearest modulus and its nearest angle, and hence this is a different rounding function. And so we consider the point-to-point reachability problem for rounded dynamical systems. We'll need to consider several rounding functions and several restrictions on the type of system allowed. We'll be interested in solving the problem for several rounding functions. In particular, we'll want to use the polar rounding function or the argand rounding functions. Here we'll differentiate between only using the floor or the ceiling function, which we call truncation or expansion, and the nearest rounding function. In full generality, we want to solve the problem for any rounding function, providing this rounding function has some reasonable behaviour, such as bounded effect. This arbitrary bounded effect rounding encompasses all the previous rounding functions, so this is what we'd really like to solve. However, we'll need to consider several restrictions. We start by considering different restrictions on the matrix. For hyperbolic systems, we show p-space completeness. Hyperbolic systems are systems which we can show that every dimension is either expanding or contracting. Note the contrast to the unrounded setting. There, everything is decidable in polynomial time, whereas here we have a p-space hardness result. Formally, hyperbolic systems are a restriction on the eigenvalues. When we remove this restriction on the eigenvalues, we are unable to solve the problem in full generality. However, when the matrix is already given in Jordan normal form, we're able to show decidability for the polar rounding function and for the argand rounding function, restricted to truncation and expansion. Even for the case of nearest rounding, and in particular for bounded effect rounding, we leave the problem open. When not in Jordan normal form, the problem remains p-space hard. In this talk, we'll look at the p-space completeness result for hyperbolic systems, the x-space result for polar rounding functions, and we'll take a look at a surprisingly simple open problem for the argand nearest rounding function. So let's look at these hyperbolic systems. So the matrix M is hyperbolic if no eigenvalue has modulus 1. And here we can show that the point-to-point reachability problem is decidable in p-space. Let's take a look at the key idea of this proof. We're going to show this for arbitrary bounded effect rounding functions. Let's assume that the maximum effect of the rounding function is delta. First, let us make the simplifying assumption that we're working in just one dimension. In one dimension, the point xi is computed by the previous point times by the matrix followed by rounding. However, in one dimension, a multiplication by a matrix is just a multiplication by a number. A one-dimensional matrix is just a number. Because of the effect of rounding, we know that this result will be in this interval. This is between the true value without rounding minus delta and the true value without rounding plus delta. Let's assume first that the multiplier is larger than 1. We want to show that once you're large enough, you'll keep on growing and you'll never come back. Observe this is not true if the numbers are too small. So for a small number, when you apply the matrix, you will grow, but when you round, you may end up smaller than where you started from. However, for a sufficiently large starting point, the multiplication will outstrip the additive effect of the rounding. And so even if the rounding takes you lower, you'll still end up larger than where you started from. And so providing you get past this point, and you get past the target, you know you will continue expanding forever, and you'll never come back and hit the target. We can conduct a similar analysis if the multiplier is less than 1. If you start at a small number, the effect of the rounding may take you larger than where you started from. But for a sufficiently large starting point, the reduction caused by multiplication will outstrip the increase caused by rounding. And so you'll end up smaller than where you started from. This means there's an upper bound on how large you can grow, because once you get to this bound, you'll start contracting again. Putting these together, this means we can always find an interval, which, once you've left this interval, you can be sure that you'll never come back to the target. Or in the case where the a is less than 1, you'll never leave this interval in any case. Because we are working in a rounded space, there are finitely many points in this interval, and so each of the points can be explored explicitly. Recall this was all for one dimension. In multiple dimensions, what we need to do is compute such a C for each dimension. Indeed, this is possible, and we show that the C you find in each dimension is not too large, and the resulting space that needs to be explored can be explored in P space. And this shows we can decide this reachability problem in polynomial space. Let's move on to show why the problem is P space hard. This is in contrast to the point-to-point reachability problem in the unrounded setting, which can be solved in polynomial time. The idea here will be to solve the quantified Boolean formula problem in the dynamics of our system. Let's take a look at the key ideas of the problem. To encode a quantified Boolean formula, we're going to need to be able to conduct Boolean expressions. Let's assume our points in space are restricted to just 0 and 1, representing false and true. And we need to be able to implement and OR. So how might we implement the AND function? I claim that this function implements the AND function, and let's see why. If both xj and xk are 0, then the result is a third, and after taking floor, we end up back at 0, which is false. If either one of xj or xk is true, we're at 2/3, and so the formula is still false. After taking floor, we get 0. However, if both xj and xk are 1, i.e. true, we end up with 3/3, and after taking floor, we end up at 1, representing true. However, we need to encode this into a matrix form, and this can be done like this. We have a dimension that is always 1. In each update, it's multiplied by this vector, which ensures that 1 is mapped to 1 in each step. To encode that x1 is x2 and x3, we use this vector, which after rounding implements x2 and x3. Similarly, we can implement OR. Instead of using a third, we can use a half, and this means if neither are true, we get a half, which rounds to 0. If either are true, but not both, we end up with 2 halves, which rounds to 1, i.e. true. And if both are true, we end up with 3 halves, which rounds back to 1, i.e. true. Similarly, we can also implement negation and constants. Together, these are logically complete, and that means providing we can compute multiple computations, we can compute any logical formula. In a standard dynamical system, if you want to apply the effect of F2 and then apply the effect of F1, you just need to multiply the two matrices together. However, here we require rounding to occur between each application of the matrix, and so it's not sufficient to simply multiply the matrix together. And so to do this, we duplicate the variables. The application of F1 will map the first set of variables to the second set of variables, and the application of F2 will map the second set of variables back to the first set of variables. So embedding the matrices into one matrix in this way, multiple applications of this matrix will implement multiple steps of the computation. In particular, this means we can implement branching. We can implement if then else. This leads us to a simple programming language whose dynamics can be embedded into the dynamical system. Here we're given an input vector x and a target vector y, and we have a while loop which operates whilst ever x is not equal to y. We then apply several functions in succession, where each function is some combination of Boolean functions. Hopefully you can see that this programming language is reasonably powerful. It operates on Boolean variables with a while loop and branching. And in fact, the halting problem for this language is sufficient to implement quantified Boolean formula. The details of this can be seen in the paper. We've therefore shown that for hyperbolic systems, the problem is p-space complete. And indeed, this p-space hardness result applies to general matrices, not just hyperbolic systems. Let's now look at the non-hyperbolic setting. Let's first take a look at using the polar rounding function on matrices given in Jordan normal form. Here we'll show decidability. So what does it mean for a matrix to be in Jordan normal form? The matrix is given by several blocks along the diagonal. Each of these blocks represents an eigenvalue. In each block we have that eigenvalue along the diagonal and ones along the upper diagonal. All other entries of the matrix are 0. A matrix is the combination of multiple Jordan blocks, each with different eigenvalues and possibly different dimensions. So this example is 2 blocks, one with dimension 3 and one with dimension 4. Let's consider what the application of a single Jordan block does to a set of variables. For multiple Jordan blocks, we'll simply repeat the analysis for each block. In the bottom dimension, x1, the application of lambda simply multiplies x1 by lambda and then rounds. In the higher dimension, we multiply x2 by lambda and x1 by 1. And so the result is to apply this dimension by lambda and add the dimension below, and then we round. And this applies for all subsequent dimensions. If lambda is not 1, we can use the ideas from hyperbolic systems. If lambda is larger than 1, eventually we'll grow past the target. If lambda is below 1, there'll be a bounded region which we cannot escape. And so we only need to consider the problem when lambda is of modulus 1. This means lambda is 1 e to the I theta, and therefore lambda represents a rotation in the complex plane by the angle theta. Let's take a look at what happens in the bottom dimension. This means we're just looking at the bottom dimension, so we're applying lambda and then rounding. So this means if we start at x0, we rotate by lambda, and then we round. And this generates the next point in our dynamical system. We then do this again. We rotate by lambda, and then we round. Observe from here on out we'll never round the modulus again. There's nothing about a rotation which will change the modulus, and so we'll stay on this modulus. Further, each subsequent application is symmetric, and so at each step we'll round by the same angle. Because there's finitely many points at each modulus, eventually we'll hit one of them again, and this means the behaviour of the bottom dimension will become periodic. And we say that this bottom dimension is just rotating and periodic, i.e. it never changes modulus again, and each step can be characterised by a rotation. Now the rotation is by an angle which is a multiple of the admissible angles, not by the original rotation angle. Now let's take a look at what happens in the next dimension. Let's assume the dimension below are the points depicted in orange. These points will be forever just rotating and periodic. And we now consider the second dimension. This dimension consists of rotation by lambda and adding the dimension below. Let's assume we start here. We rotate by lambda, we add the dimension below, and we round. This addition of the dimension below corresponds with this vector here. In the next step, we rotate by lambda again, we add the dimension below. This now corresponds with the next vector from the dimension below, and then we round. And we'll keep repeating this process. We're going to take a look at the angle between lambda x and the dimension below. Observe this angle is what determines the growth in the modulus. The dimension below is of a consistent modulus forever, and the rotation does not affect the modulus. And so the only thing which will affect the modulus of this dimension is how well aligned this vector is. And the more aligned it is, the larger the growth will occur. Observe in the next iteration, these vectors were more aligned, and so the modulus grew more than in the last iteration. In fact, we show that this always occurs. In every step, this angle never increases. And so once the modulus starts to increase, the modulus will increase forever. And so we can say that this dimension is either expanding, or if the dimension below is so insignificant that it never causes a change in the modulus, then it may be just rotating. And this dimension will never increase in modulus. If this dimension is expanding, we can simply wait until this dimension hits the target, or goes past the target, in which case we'll know we'll never return again. However, if this dimension is just rotating, we can treat this dimension like the dimension below, and we can move on to the next dimension. And this shows decidability for the polar rounding case. Similarly, one can show decidability for Argand rounding when the rounding corresponds to either taking the floor function or the ceiling function. But the problem remains open for nearest rounding, even in Jordan normal form. Throughout this talk, we considered only whether the dynamical system hits a target which comprises of a single point. However, it can be interesting to consider whether a dynamical system hits a more complicated target. One such example of these would be a bounded polytope, i.e., does the orbit ever fall somewhere into this region? Indeed, we can extend our results for any target which represents a bounded region. There is a finite number of integer points within any bounded region, and so we can simply ask the point-to-point reachability problem for each one of these points. We may also be interested to ask whether the dynamical system hits an unbounded region. For example, we might ask whether it hits a d-1 dimensional hyperplane. In our two-dimensional visualization, this represents a line in space. Or in a three-dimensional space, you could consider whether it hits a particular plane. However, this problem is analogous to the Skolem problem, and is a long-standing open problem in the unrounded setting. In the unrounded setting, the bounded polytope problem also remains unsolved. However, there the rounded variant simplified the setting. For the Skolem problem, this isn't the case. In fact, the Skolem problem remains unsolved even for integer dynamical systems. And this means if we treated that dynamical system as a rounded instance, the rounding would have no effect. And so, in particular, these problems remain hard even in the rounded setting. Similarly, we can ask the problem whether we ever hit a particular half space. Like the Skolem problem, this remains unsolved in the unrounded setting, and similarly is hard even for integer systems. And so this problem remains open. So the Skolem and positivity problems are not candidates for future work unless new progress is made in the unrounded setting. Let's now take a look at the open case for Argand rounding. Here we're going to show a very simple instance of the problem which is still open. Let the matrix be simply a rotation matrix on a two-dimensional plane. and let the rounding function be the nearest rounding function. Without rounding, the orbit is simply a circle, here depicted in green. However, with rounding, we cannot infinitely often stay on the circle, and so from time to time, the rounding will take us up in modulus, and from time to time, it will take us down in modulus. However, it remains open whether this happens in a periodic manner, or if the points can grow arbitrarily far and then return. We conjecture that such systems are eventually periodic. This is especially intriguing that such a seemingly simple, low-dimensional instance of the problem appears so difficult to analyse. This is also related to a question of periodicity in discretized rotations as proposed by Vivaldi in 2006. Thank you for listening.